who are attending, who are not attending. Because when none other list is there, once after I end the session, I would able to download this list. Who are all joined, when they joined, when they have disconnected, everything, the data will be with me. You also send me overall not attending in regular, because taking each file and comparing who attended in which day and other quite difficult. So that's why if you would have something, if you are sending this data to someone else, you just forward the same data to me so that I would confirm overall not attending in regular. Okay.
Okay, sir.
So the next access control method or multiple access method is channelization. Okay. So the channelization is actually a multiple access method. So in which the available bandwidth of the link or the wire or the or or what you call channel is shared in time or in frequency or through the code between the between different stations. Okay. So in this part, we were mainly discussing some of the channelization protocols. One is frequency division multiple access. Then that's what we called as FDMA. And we have another multiple access method called TDMA, time division multiple access, and another one is code division multiple access. So this part is not included in your syllabus. From here, the channelization will not be there for your syllabus. So I'll just brief you about this protocols, and you will study this in detail in the mobile communication. Probably we might be using FDMA and 2DMA in 1G and 2G. Later on in 3G, we start be using CDMA, code division multiple access. I think you all this study all these things in that course. So that's why I'll just only brief you. I'll brief you about what all this multiple access method are. Okay. So we see the application of all these methods, whatever we saw in chapter. What I mean by chapter here is in cellular networks, the same thing we were just explaining them. In the cellular mobile system, actually this channelization methods are used. Okay. So the first one is frequency division multiple access. Okay. If you would trying to understand this multiple access in the context of computer networking, probably you can see them like this. So where you would have a broadcast channel, a common channel. So where n stations were connected. So the available bandwidth is divided into frequency band. Okay. So what was the available bandwidth that we would have? So that will be divided into frequency band, so that each station is allocated a band to send its data. So you can see here we would be having different frequency bands, and each band of the frequency would be allocated to each station, so that a station can send the data in that frequency. Okay. Uh, so in other word, I would say each band is reserved for a specific station. Okay. If you would have n station, then you should have n frequency band, so that each band of frequency would be specific, like reserved for the specific station to send their data streams. Okay. Here, so then it is that frequency band is belongs to them for all the time. So any time if any station has data to send, so it can use the frequency for the data transmission. Okay. Then each station can also use a band passer to confine the transmitter frequencies to station for the data to get inference, what's the data being sending in its adjacent band, frequency band. So then each frequency band gets separated the what you call we give a small gap between them, each frequency band, and that's what we call the guard band. Okay. So what you would see the space among each of this frequency band, we call them as guard band. So that frequency we will not be using. Okay. So what do you mean by that? So whatever the bandwidth that we would have, so that will be divided into number of frequency band, and each band, let us say this one is F1, F2, F3, F4. Each of this, between them, some frequency we not be using, and that we call them as guard band. Okay. Okay. So in FDMA, special predefined frequency band entire period of communication. This means the each station can send data continuously or sending the stream of data to destination at any point of time. So that will be the frequency is completely reserved then. Okay, go now. So whether this FDMA and FDM, frequency division multiplexing both are same. This is frequency division multiple access method. Where is another uh, techniques we use what is called frequency division multiplexing method. These two things where you will branch, but there will be difference between them. There is a difference between a frequency division multiplexer and with the frequency division multiplexing, frequency division multiplexing. In FDM, vertical layer technique, so it combines the signals low from the low band and transmit it to the high band. So FDM means so it means that it is a vertical technique which helps to combine the load of a lower bandwidth where the signals are combined on low pass. Okay, so which means needs a physical multiplexer which modulates the signals to combine them and create band pass signal. Okay, the bandwidth of the channel is shifted by the physical multiplexer what we would have in the layer. But actually we call them as FDM. Okay, but if you see this FDMA technique, so this is an actual access method which operates data link layer. This data link layer in each station is FDMA. But in TDMA, the complete bandwidth could be utilized based on the time, different times. Okay. So in TDMA, each station can share the bandwidth of the channel in the respective time. So each station is allocated with a time slot during which the station can send their data. Okay. So let us say if you would have in this example, you can see there were both stations are connected to common channel. So then the
Sir,
complete the available
sir,
bandwidth. Yes.
presentation not visible.
Yes.
Presentation ಬರ್ತಿಲ್ಲ.
ಹೌದಾ? But I presented. Okay. Okay. It's now visible.
Yes, sir.
It's now visible. Okay. Okay. So here, so we were able to share uh, based on the time slot. Okay. Each station would be allocated with specific time slot so that during that time slot they can use this channel for the transmission of data. So main problem with the TDMA lies in achieving the synchronization between the different stations, isn't it? So each station needs to know when is the beginning of its slot and the location of its slot. So that was the main problem. So because of this may even difficult because of this propagation delay which is introduced in the system. Okay, with the system stations, if the stations are spreaded over a large area, so we may not be knowing what was the propagation delay, and in order to compensate that delays, so we were inserting something called guard time. So each you can see each of these time slots would also have some guard time, so that during that time this plan will be something not being utilized. Okay. So it is what we called as TDMA. So we will also find out what was the efficiency and all for this multiple access method, but it is something out of scope. Okay. In TDMA, the bandwidth is just a one channel and that is used based on time share between the among different stations. Okay. There is another multiple access method which is quite commonly used nowadays is CDMA. So one channel. So how the CDMA was differed from FDMA and GDMA. So obviously this were differed from both of this multiple access method. So before let's see them, so we'll understand what was the analogy of the CDMA is about. Okay, having one room and let us assume there were so many people are there inside and all of them were talking, but I used to tell them all of them should talk with a different language. Okay, so there were so many groups I can made in one room, and each of them will talking at the same time. Okay, and at the same loudness. Okay, but I said them to use different language. So among this groups, overall they're talking. They should not talk with the same language. Okay, so they should talk their different language so that where so we were able to at least listen what they were talking and we would also be able to understand. So that is what analogy what we were using in this CDMA. So what it means, the one channel can carry all the transmission simultaneously. So we use the complete bandwidth. We were not going to divide them into separate frequency band, and we will also not share that bandwidth among the time based. So we will use the complete bandwidth and all the time and all the stations were could able to transmit the data. Okay, that is what the CDMA is approach. Okay, you can see here, let us assume there were four stations were connected to this common channel where I'm assuming all of them would have the data to send and I represent this data as D1, D2, D3, D4 for the respective stations. Okay, and I just multiply this data with some. Okay, each station should multiply product the data with this some code. And what was the sum that you would get when they put all this data into a channel? It is actually a sum of all its data, right? This code is actually representing the language which is chosen by them to talk. You should understand like that way. So there is a room where I leave like four people inside the room, and I've asked them to talk. Even both where they can talk simultaneously, but they should not talk with the same language. Okay, these two they can converse by using Kannada, and these two they can converse by using in English. Okay, but they should not talk both of them by using Kannada and Kannada, or they should not talk both of them are using English and English. They can talk at any time. Even these people would also talking. Okay, but they should use a different language. Okay, that is what the analogy here. So both all the station can send the data simultaneously at the same time by using the complete frequency bandwidth of whatever the channel that has. So, but it should use a different set of codes when they are sending the data to a common channel. So here is what C1 it's used. Here let us represent the code used by station 1 is C1 and I station 2 is C2, 3 and 4. As that send their data, the sum of all the data is actually being I used to represent them in the channel. Okay, it becomes D1 and C1 plus D2 and C2. Okay, and plus D3 and C3. Uh, D3 and C3, and there is something called D4 and C4. Okay, this was uh, the sum of the data after all the stations were sent over to the channel. Okay, so this was the code. I just wanted to say what would be the code used by each station, and this data would be multiplied with the actual data. Like this code will be multiplied with the actual code. If you see them, if this code, if all these codes are an orthogonal in nature, what do you mean by that? So this code has some properties. So what is that property? So when you multiply one code with another code, we supposed to get the product as 0. And if you multiply a code by itself, okay, C1 into C1, if you have a product of this C1 and a C1, you will get the product as 4. Okay, that's what this properties. So the properties of this code when and we should be generating it in a way and that is being used by the each of the station before they are sending the data. What is that property is? So the code should when the code multiplied with another code, we will get the answer result is 0. When a code is multiplied by itself, we will get product. Something here, y will get, I should get product as n, where here it is 4, because that 4 represent the number of stations that are connected to Gen network. So this, the elements that we would have here, it should depends on the number of stations that we have. The each code is a sequence. It have some elements in that sequence. So each element, the number of elements in this array will depends on the number of stations that we have in this network. Okay, if you have 10, then probably your sequence element should be 10, like that. Okay, and how to generate? So we will look at it later. I think that is out of scope. And before that, we will make some assumption that the data representation in CDMA. So how is data would be represented or encoded here? The data bit 0 is actually encoded as -1. Okay, in signal, encoding your data bits binary into the signal is given -1 volts, and representing this data one bit 1 as positive volts. Okay, and if there is silence, if that is nothing, then it will be encoded to the 0 volt plus -1 volt, 1 volt, and 0 volts. That is what we were encoding your data into the signal. Okay, so later let us assume in an example we would know how this code been generated. Okay, so this was the C1, C2, C3, C4, and let us assume that station A is sending bit 0, station 2 is sending bit 0, and station 3 is not sending anything. Station D is sending bit 1. So I have to encode them into signal, right? So that it is -1. So -1, 0, then +1. So what the next step? This data, this element should get multiplied with C1. If you multiply them, you will get -1, -1, -1, -1. If you multiply this with this, -1 plus 1, -1 plus 1. If I multiply this +1 -1, -1 plus 1. If I multiply this, I'll get the vector as all zeros. And I have to add all these things, right? If I take this into a channel, if what is that here? It should be sum of all C1, D1, D2, C2, D3, C3 plus D4, C4. If I add them, I'll get the resultant the equation. The resultant sequence is minus 1, -3, +1. Okay, this was the resultant. Okay, if you want to find what is the data being sent by any of the station, let us say if I want to check what is the data will be sent by station 2, the station will receive this sequence and you will multiply by the code code of the station so that it would able to decode what is its the data being sent by that particular station. If I take this -1 -1 -3 +1, okay, and if I multiply this with, okay, the code of this D2, okay, D2 is what? -1 and add, you should add, okay, +1 -1 +1. If I add, you will get what is called 4, something nearly 4, okay, -4 you will get, and if I divide that with the total number of stations that which is connected here, you will get as -1. And if you decode it here, you'll get to know if -1 is actually the representation of bit 0. Okay, so like this way we used this CDMA. So you can see here how this would be represented after you product of your bit and the code sequence. So this will be represented the signals like -1 volt, -1 volt, -1 volt, -1 volt. This would be -1 +1 -1 +1. All of them are 0 here, and here it is a +1 -1 -1 +1. And if I add them, so you will get a -1 -1 -3, then the +1. Okay, you can see here now. If you want to see what was the station's 3 words ending, is actually station 2. You just change it. Station 2. The data is like this: -1 -1 -3 +1. And the code of the stations 2 would be -1 +1 -1 +1 -1. So you'll get the inner product resultant gives -1 +1 -3 -1, and summing of all this value you would get -4, and -4 divided by total number of station you will get -1, and we know the data representation of -1 is actually bit 0. So this is how we were able to we get the what was the data being sent by the station in this common channel by using this CDMA techniques. Okay, how this code was generated? So we use the general rules and an example to create this code by using Walls table. Okay, Walls table. So the first one we defined W of 1 is actually the +1, the metric of +1, and W of 2 power n could be written as Wn Wn Wn, and the last element would be the complement. Okay, this is how we write. Okay, and we know that W1 is actually a metric +1. Okay, W2 I can write them as is actually if I multiply 1 here, it is W1 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 and W1 complement. So that will becomes +1 +1 +1 then -1. So if you have two stations, then you could use this row as C1 and I could use this row as C2. If you have four stations, then I should have at least four code sequence, right? Then it will becomes okay. So the same thing, this one W2 W2, so W2 then W2 complement. So that will becomes is it 2 in that is 2 into 2, right? So W2, so that W2 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 complement. So it will become +1 +1 +1 -1, which is telling what is called W2, and same thing would be here +1 +1 +1 -1, and here it is +1 +1 +1 -1, and the complement of this is -1 -1 -1 +1. So here it would give the four rows so that this four rows could be used as four code chips. This is what we call as chipset. Four chips, code chips, and we are assigning this to each of the station. You can see the elements of that first matrix would be +1 +1 +1 +1 +1 -1 +1 +1 +1 -1 -1 +1 -1 -1 +1. So there were four codes chips. So this could be used for each of the stations to assign, and there were orthogonal in. If you take any code like C1 and C2, if you multiply them, you will get the resultant as 0. If you multiply C1 and C1, you will get 4. Either if you get multiply C2 and C2, you'll get 4. If you multiply C3 and C3, you'll get 4. C4, C4, you'll get 4. If you multiply C1, C2, you'll get 0. If you multiply C2, C3, you'll get 0. So that was the property this it gives us by following this false table general rules. So then the number of sequences in Walls tables needs to be n, which is n is equal to 2 power n. So there were some questions here. Find out the chips for a network having the 2 stations and 4 stations. Just what I've written. For 2 stations, it is plus 1 Walls table W of 1 if I write them. Plus 1 plus 1 minus 1. Okay. So plus 1 could be C1 and plus 1 minus 1 could be C2. Okay, that is what the first one chipset. For 4 station, it is what we written the table, the metric. The same way if you write and use for each row, it could be the each different code for this each stations in this network. Okay, and what was the sequence we would? What is the number of sequence if we need if you have 90 station in our network? So m is n, which is 2 to the power of 7, which is n is equal to 2 to the power of m, right? M is, I need 2 to the 7 to get 90s. This is approximately 128. We can use them 90s and another chip sequence we could use for later. That's it. And to the receiving station, getting that what we did, the same thing. Through that, the receiving station can get the data sent by the specific sender. If it is multiplies the entire data on the channel by the sender chip score. So then it is divided by the number of stations, you will get actually that will be the solution for the how a receiver station would comes to know what was the data sent by a sender. After if you multiply the product result into that sender code and divided by the number of stations, that will give the what the data will be sent. This was the proof that you multiply with this, you will get D1 into C1 to C1 plus D2 into C1 into C2, and we know that the set of a code would be when you multiply C1 and C2, you get a 0. So then this would also be 0. This would also be 0. Okay, this would also be 0. So the whole term becomes 0 here. When I do C1, you will get n. N I said there in 4, right? This is actually n. So n into D1. So what is the product you get when the resultant multiply with some specific code, you will get D1 into n. And if I divide that with n, you will get what actually the D1 is. Simple calculation. When we divide that resultant by n, we will get D1. So that is all about this code division multiple access method. Is it clear? Is it clear? Any doubts so far? So this would complete of a unit, so not of 60% of your second unit. So the next we will looking at wired LAN, which is called Ethernet, and was standard made by IEEE. Okay, so I'll stop this and I'll continue with the next one. Okay, this from here it is a part 2 of your second unit. We were discussing about wired LAN, which is called Ethernet. Okay, so first, and we already discussed so much about wired LAN, right? What is wired LAN? What was the topology, and all those things. Okay, we will now look at the standards, which is given by IEEE. Okay, in 1985, the Computer Society of IEEE they started a project called a project 802.2, and this project is mainly to give the standards to enable this intercommunication. Okay, so among the equipment from the varieties of manufacturers. So why we need this standards? Because later in 1855, So each manufacturers they were using their own standards, and that standard would be only interoperable with its own equipment were manufactured because they would also use the same standard. So I would able to intercommunicate the device which is manufactured by HP with the device of HP itself. So there will be no standards which are defined between the equipments which were manufactured by different vendors. Means we don't have a universal standards. So in 1855, so the IEEE have been started a project which is 802 dot sorry 802 to set a standard and which enables for the intercommunications among equipments which will be manufactured by so many vendors. So this project 802 is just the way to specify the functions of the physical layer and the data layer. Okay, so of the major LAN protocols, because when we say uh, whatever the protocols we see, that's only the protocol with respect to physical layer and the data link layer. The rest, what we have the above layers, network and whatever transport and application layers. So there are something they will already be standard where whatever you would see respect to wired LAN or wireless LAN, it's only specific towards to the bottom two layers. Okay. Okay. So here 802 is the way of specifying the functions of this physical layer and the data link layer. Okay. So of this major LAN protocols, this project 802 does not seek to replace any of the part what we would understand in the OSI model or in the TCP/IP model. Okay. So the later after they would made the standards, okay, the standard been adopted by ANSI, American National Standard Institute in 1987. Then your International Organization for Standardization would also approve, and it was now an international standards under the designation of ISO 8802. Under this, so now whatever we saw, we seeing it in wired LAN, so it's standardized under the project of 802, and that would also approved and adopted by ANSI as well as for ISO. Okay, so this figure is actually is trying to show the relationship of your 802 standards and the traditional OSI model. Okay, so what you could see here, we know that the OSI or TCP/IP model, they have this physical layer, data link layer, and the above upper layers. So we were only trying to show you here the standards with respect to the physical and the data link layer. Okay, so where in IEEE standard, which is 802, they have subdivided this data link layer into two sub layers. We already discussed it, LLC, and we have something called media access control. Okay, so and also this IEEE is also created a several physical layer standards for different LAN protocols. So I would say if you would use Ethernet LAN as a star and something, whatever the standard that we would have right now, it would follows the Ethernet standard, physical layer standard as well as the MAC layer. Okay, but if you would have something like the ring topology and based on that, so probably we might be using of the standard ring token ring physical layer standard, and we would also use the multiple access method as token passing. Okay, and similarly we would be using a token bus would also be one of the standard we use earlier, and for that we would also use a token bus MAC layer protocol. And similarly, we might be having there were the several uh, Ethernet standards, and depends on the way in which we were connected and what how was being used. Okay, because obviously the physical layer standards will be different because in the physical layer we mainly define about the multiplexing, what was the line coding techniques, and what is the modulation technique, all these things we use. Okay, since that would be different for each of this. Uh, Either it be an Ethernet or it could be token ring or token bus or even some different kinds of networks. Okay, so we will mainly looking at the Ethernet and its standard with respect to the physical layer and the MAC layer. Okay, because LLC we would already know that it is responsible for framing, flow control, and error control, and this would be remain same for all these different standards what we have. We don't have any particular or in specific proprietary protocol under this these two layers. So it is depends on the way in which that the network been built. If they are built in ring based something, you might be having a ring token ring physical standard and the token passing method as media access control method. Similarly, for that would also be used in token bus kind of network. And if you would have something a star or bus kind of network, we will be using an Ethernet. And where for every standards what we have here, this would be kept as common. Okay, flow control, error control, framing, all these things are common to each of these different specifications. Okay. Okay. So we will now discuss only with respect to this Ethernet and why we would have something star and how that will also evolve from the bus topology and why we would use now something called topology we used to use on connecting all hosts to in a LAN. Okay. Okay. So here, why do we need of? So we're just comparing the SDLC frame with LLC and a MAC layer. Okay. This is actually an SDLC frame. So this is actually data link frames what we use, but we will not discuss this. I don't included this into a syllabus. If I put this into a syllabus also, it should be too lengthy. That's why I have not included this and PPP uh, type of protocols were the data link layer protocol, but and this was the format of that frame, HDLC frame. Okay. Uh, uh, HDLC is something higher data link control frames. Okay. So the first it might have an address. Address is something tells the destination address and the source address, and it has a control field. Where in this control field, it helps to gives us the flow control and the acknowledgement. Okay. And here the upper layer data. Upper layer data is actually is what the PDU. Okay, protocol data unit, whatever we call them as frame, sometimes we would also call them as PDU. PDU is actually what the data from the upper layer, which is from the network layer. We call them as protocol data unit, or in respect to any of the specific layer, we would also call them as PDU, which is called protocol data unit. Okay, so here in address layer, okay, so this is actually a PDU. Okay, in this PDU we would be having something, a control field, then the address field. In the address field we would having destination access point and the source service access point, and we will ask the we wrap the upper layer data, and this PDU will get be encapsulated with the MAC header and the FCS. So what we said in OSI, so we would have a data which is from the upper layer. We had H2 and Tyler T2, right? This is what FCS and the MAC address. Where in this PDU, so whatever the data from the upper layer, it would again added with this address data and the control data and the upper layer data. This is actually the upper layer data. Along with that, this control data would gives us the flow control mechanism, and this will be used for addressing the destination service access point and the source service access point. Okay, okay. So no need to worry about this. I just given to compare LLC frames and MAC layer with respect to HDLC. We have not discussed about this HDLC. That's why you are not understanding this what. Okay, if I would have explained this, I think you would understand what it is. You can neglect it, no problem. Okay. So we will now look at it. What was the physical layer standards we were made and we were using today in our Ethernet LAN. Okay, the first the standards what we would say in Ethernet LAN is standard Ethernet. Okay, this original Ethernet was created in 1976 at Xerox Palo Alto Research Center. Since then, it has been gone through different generations, and we will look at each of this implementation, the common implementation with respect to each of those different standard like different generations. Okay, so traditionally we call them as standard Ethernet as traditional Ethernet, and this was the first we were started with. We call them a standard in 1976. Okay, so and later we evolved and we used to call them as fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet. Okay, so before getting into this, okay, let me show you this Ethernet evolutions over here. Okay, here I would say we were having first as the standard, then we would made some other changes and we were able to get the data rate around 100 Mbps. We call them as fast Ethernet, and we would also get a much more faster. Okay, with the availability of all this and all this, what were the seeing the evolutions? All this were back compatible with the original one which we used earlier, standard Ethernet. Okay, so they use something gigabit Ethernet where the data rate is nearly equals to 1 gigabit, and we use something 10 gigabit Ethernet. We were able to get the data rate of around 10 GB per second. Okay. Uh, so before I'm getting into this, each of this physical layer standards and its implementation. So let first like directly get into our MAC layer standards. Okay. So MAC sublayer standard. Here in a standard Ethernet, where a MAC sublayer governs the operations of this access method, and also the frame data is received from the upper layer and it passes them to the physical layer. This was the standard frame format defined in your wired network in wired LAN. So what was the standard? We so far we are not see the frame format, right? So far we are nowhere we saw the frame format. We simply keep saying that frames, 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 but we never discussed what was the data and what all the additional information we've been adding to this frame in order to get all those things. Means flow control, error control, all these things, right? Okay, this is what the standard made by the IEEE under this 802 project is. The standard frame format of this wired LAN, it should be like this. Okay, and we call this as 802.3 MAC frame. Okay, when it is the MAC control, MAC when it comes to MAC sublayer, after this LLC, we have a MAC sublayer, right? Here, this how your frame should be look like this. Means it should have a 7 bytes of preamble, and it should have 1 byte of this is what the flag. So we saw that right when we do framing. So we had a framing and a header, then you have data, then again you have the flag. Okay. Okay, so this what SFD is actually start of frame delimiter. SFD means start frame delimiter. Okay, so and it's of how much bytes? 1 byte. So this is 7 bytes is actually preamble. Preamble is something we were. This is not actually data or even it is not any other information. Control information is just a preamble. It is of consist of 56 bits, and how they were in alternative ones and zeros. 101010 alternative of this, how many bits you would have? 56. That's of totally 7 bytes. Soon after that we have the start of delimiter, start frame delimiter, which is actually called as flag. So ಅಲ್ಲಿ ನಾವೇನಂತ ಯೂಸ್ ಮಾಡಿದ್ವಿ, we said 0 followed by 6 ones, then again 0, that as we assumed as flag. Here how what they have taken 10101011, the sequence they have taken, that depends on the protocol. Okay, So this could be either, the flag could be either this also, or even it could be this also. It is not matter, right? After this, we have a 6 bytes of destination MAC address. So destination MAC address 6 bytes means 42 bits. The MAC address of your destination, then the MAC address of your source, and there is a 2 byte of length or type. Length or type, this having a dual role now. Either this could be access length or it could be access a type. So if they access a length, then it defines the length of this frame, which having 2 bytes. Okay, if they defines a type, which helps to define what will be the upper layer protocol would be used. So then that time it will be used acts as a type. It depends on the applications that what this MAC layer has been used. So they later will explain you what is length field and what is type field. So and then after we have something called data and the padding. Data and padding. Why here in wired LAN? If we should need a minimum of frame size. If you don't have minimum size, then you will do the padding because we use a CSMA bar CD. CSMA bar CD, as soon as sending the data, you would also listening for collision. Then you should have a minimum of data frame. Then you have the error detection mechanism, which is called GRC, cyclic redundancy check, and that's of 4 bytes. So this is what the format you should write, and also you should know what was the size of each field. Okay, so this we also called as 802.MAC frame, or we would also call them as Ethernet frame. Ethernet frame ಅಂತಂದ್ರೆ ಒಂದೇ 802.3. So for wired LAN, they given the standard with the 8 project 802.3.3 MAC layer. Okay, and this complete standard for 8 Ethernet wired LAN is actually 802.3. For wireless, it is 802.11. Okay, for different networks, they have different standard. Probably for token passing, token ring, they used .4. For token bus, they might use .5, like that. For every different network, they will use different names for their standard or their specification. For wireless, they use 802.11. Okay. For this one, Bluetooth, they use 802.15. Then Zigbee, they use 802. Something. Okay, like that. Then WiMAX 802.16 something they use, like that. Okay. So from here later we'll discuss in next class. I'll stop here. If you have any doubts, you can ask me. I'll wait for 2 minutes.